This also we had done. Open loop versus closed loop. Toaster example we had given. Temperature control systems we had discussed. Then the next thing is computer controlled system or digital control system. So in this, a digital computer is works as a controller. This also we had done. And this is a typical control system of an industrial process. So basically, what are the terminologies of basic control systems? Is that it is a plant or a process which we need to control. The inputs are the excitation or stimuli and disturbances to the system, which may be known or unknown. The disturbances are the unwanted inputs to the system. Outputs are the response of the systems. Sensors are the measurement which they measure the system variables such as excitation and response. Actuators are the systems which drive various parts of the system. Controller is a device that generate control systems. Control law is the relationship or scheme according to which the control signal is generated. And the control system is plant plus controller, which includes sensors, actuators, and signal conditioners. Feedback control signal is determined according to plant response. Feed forward control, no feedback of plant response is given to the controller. Okay, so these are the basic terminology. Then we can take another example of a closed loop control system, which is elevator example, to get a better understanding of the response characteristic of a control system. So when the fourth floor button of an elevator is pushed on the ground floor, the elevator rises to the fourth floor with a speed and floor leveling accuracy designed for passenger comfort. Okay. So the physical entries cannot change their states instantaneously. Thus, the elevator undergoes a gradual change as it rises from the first floor to the fourth floor, right? So it is a gradual change. That is the transient response. So from here to here, from 0 to this point, it is called the transient response, right? So after the transient response, a physical system approaches its steady state response. That is, elevator reaches the fourth floor. So this is the steady state response, which is an approximation to the desired response, right? So the accuracy of the elevator's leveling with the floor could also make the output different from the input. We call this difference as steady state error. This is the difference between the input command and the steady state response is the steady state error. So steady state error must design to be zero for some applications such as robot inserting a memory chip onto a board. So this error is a critical variable. So a control system is dynamic. It responds to an input by undergoing a transient response before reaching a steady state response that actually generates the generally resembles to the input. The transient response is important because a slower response makes elevator passenger impatient, while an excessively rapid response makes them uncomfortable, right? So if the elevator oscillates about the arrival floor for more than a second, a discomforting feeling can result. Transient response is also important for structural reason. Too fast a response could cause a permanent physical damage. Thus, we analyze the elevator for its transient response, and if we need, we adjust parameters or design components to yield desired transient response. Right? The steady state response of the elevator is its location reached near the fourth floor. An elevator must be level enough with the floor for the passenger to exit. Thus, the elevator's steady state error should be analyzed or designed corrective action to reduce the steady state error as low as possible. So the statement of the problem is that the discussion of transient response and steady state response is moot if the system does not have stability, right? So the system must be a stable system. So actually the total response of the system is natural response plus forced response. For a control system to be stable, a natural response must eventually approach zero, thus leaving only the forced response, which is an approximation to the input. But you have to be very careful if the natural response grows without bound and the system is no longer controlled, or the system becomes unstable, right? So instability could lead to self destruction of the physical device if limited stops are not part of the design. In our example, the elevator would crash through the floor or exit through the ceiling. Thus, a control system must be analyzed and designed to be stable. Notice that the transient response is the sum of natural and forced response when the natural response is large, while the steady state response is the sum of natural and forced response when the natural response is small, right? So, what is important in a control system? The most important characteristic is stability, transient response speed, accuracy, that is dynamic overshooting and oscillation duration, and steady state error. The fourth aspect is robustness. Robustness is basically errors in the model in presence of uncertainties and non-linearities. These are also resulted from the effects of disturbances and effects of noises, right? So this is the diagram. You can note down this in your notebook as today's lecture notes. Okay, I have told you to make a register for this course and take notes date by date. And at the end of the class, you have to upload your notes. All right, so I'm giving you time to take notes. So this is the brief view of control techniques. What are the various control techniques? Tons of research papers have been published in literature on how to design a control laws for various control purposes. So they can be roughly classified into following techniques. One of them is classical control, which is normally used as proportional integral derivative or PID control. It was developed in 1940s and used for control of industrial processes, for example, chemical plants or commercial aeroplanes. Okay. So optimal control are the linear quadratic Gaussian control, LQG, Kalman filter, H infinity control, developed in 1960s to optimize a certain cost indexed and boomed by NASA Apollo project. Adaptive control use online identification of the process parameters, thereby obtaining strong robustness properties. Adaptive control was applied for the first time in aerospace industries in 1950s. Robust control are H infinity control developed in 1980s and 90s to achieve robust performance for stability in the presence of small modeling errors, for example, military systems. Nonlinear control are currently hot research topics developed to handle nonlinear systems with high performances, for example, military systems such as aircraft, missiles, etc. Intelligent control systems are predictive control, neural networks, fuzzy logic, machine learning, evolutionary computation, and genetic algorithms, researched heavily in 1990s, developed to handle systems with unknown models. For example, economic systems, social systems, human systems, etc. Other considerations in control systems analysis and design are the factors affecting hardware selection, that is, motor sizing to fulfill the power requirement, choice of sensors for accuracy, and design economic impact, that is, budget allocation, competitive pricing, etc. So, modeling of dynamic system is done by dynamic system is a system which response variables are functions of time with non-eligible rates of change. So models are the representation of a system, and types of model are the physical models, that is prototype or scale model. Mathematical model are analytical models using physical laws. Computers, which gives the numerical model using simulations. Experimental model using input output or experimental data. Mathematical models for physical dynamic systems are distributed parameter models, PDEs, for example, spring element, flexibility, inertia, and damping, and lumped parameter models, ODE. How to design a control system? By
And what
understanding
is
the
UDE?
automation.
Last page UDE.
lumped parameter lumped parameter model.
It's form of learned parameter model.
Yeah.
Okay.
Distributed parameter, PDE, and lump. There are two types. Na? One is distributed. Normally we do the lumped parameter analysis.
Okay.
So what are the automation requirements? Which plant or process can be used to meet the requirement? What are the specifications to be achieved, etc.? And which variable can be manipulated by the actuator? What are the output variables of interest? What should we measure? Which are the disturbances? Then choose sensors to measure the required feedback signal. Choose actuators to drive the plant. Get a simplified mathematical model or a reliable simulation model of the plant, sensors, and actuators. Synthesize the control algorithm based on the developed model and control criteria. Test the control designer analytically by simulation. Validate on real physical system, that is implementation. Repeat this process until a satisfactory physical system response is achieved. Okay, so these are the various steps for a control system design. Okay, so you can write down all these steps. These are very, very important parts of a controller. Okay, so I'm giving you time, just note down the various steps. So control systems engineers skills are uh, so many. For example, control system engineer is an exciting field in which to apply your engineering talents because it cuts across numerous disciplines and numerous functions within those disciplines. Many engineers are engaged in only one area. So a control system engineer must be good in mathematics to get a good hold of mathematical model of the process and design a controller that responds to the desired requirements and specifications. Then physics, to understand the physical phenomena of the process to be controlled, so as a good mathematical model can be found. Simulation is to analyze the control system as well as simulate its performance. Being aware of the current available technology to choose the best hardware and software for implementation of the proposed controller. Okay, so a lot of skills and knowledge to have got from a control systems engineer, which makes a control system engineer one of a kind. The computer plays an important role in the design of modern control systems. In the past, control system design was labor intensive, but using hand calculators or at the best plastic graphical aid tools. The process was slow and the result was not always accurate. So large mainframe computers were then used to simulate the design. Now, today we are fortunate to have our own desktop computers and softwares to perform the analysis, design, and simulation with one program such as MATLAB, for example. With the ability to simulate a design rapidly, we can easily make changes and immediately test a new design. Okay, you can try alternate solutions to see if they yield better results, such as reduced sensitivity to parameter changes. We can include non-linearities and other dynamical effects and test our models for accuracy. So computer-aided design tools are or CAD tools. In this course, we will use MATLAB, which is a trademark of the MathWork Inc. as a computer-aided design tool for control system analysis and design. In addition, we will make use of some additional functionalities to MATLAB, that is Simulink, which uses a graphical user interface, and the symbolic math toolbox, which saves labor when making symbolic calculations required in control system analysis and design. MATLAB is used here as an alternate method of solving control system problems. You are encouraged to solve this problem first by hand and then by MATLAB so that insight is not lost through the mechanized use of computer programs. You must go to MathWork. This is the website of mathworks.com, Academia, and read out MATLAB and Simulink handouts. Okay, so this is the history of control engineering. In 300 BC, Greek discovered the float valves and regulators of liquid level control. In 1770, James Watt gave the steam engine concept, governor for speed control. Then 1868, James Maxwell of the Cambridge University gave the theory of governors. In 1877, E.J. Routh gives the stability criteria. In 1893, A.M. Lyapunov, which is from Soviet Union, gave the stability theory based on state space formulation. In 1927, H.S. Black and H.W. Bode of AT&T Bell Labs gave the electronic feedback amplifier concept. In 1930, Robert Wiener of MIT gave the theory of stochastic process. In 1932, H. Nyquist of AT&T Bell Labs gave the stability criteria from Nyquist gain and phase margin. In 1936, Calendar D.H. Harty and A. Potter from England gave the PID control system. In 1948, Claude Shannon of MIT gave the mathematical theory of communication. In 1948, W.R. Evans gave the root locus method. In 1940, theory and application of servo mechanism, cybernetics, and control system was introduced in MIT and Bell Labs, etc. In 1959, Peitner of MIT gave the bond graph technique for system modeling. Just a minute, excuse me. So this is the history. In 1965, theory of fuzzy sets and fuzzy logic was given by L. Zadeh, and then intelligent control and nonlinear control was developed. All right. So next thing is a typical control system is looks like this, as we have already seen. The most used sensors and actuators in control systems are these: temperature, pressure, flow, level, velocity, acceleration, force, etc. So you can check this notes in your copy. These are the sensors. The actual actuators are electrical motors, pumps, valves, and heaters. You can take note.
You're supposed to do here, ma'am.
So other examples of control systems are natural control systems, which are within our body. For example, the pancreas, which regulates our blood sugar. In time of fight or flight, our adrenaline increases along with our heart rate, causing more oxygen to be delivered to our cells. Our eyes follow a moving object to keep it in view. Our hands grab an object and place it precisely at a predetermined location. So, this is again an example of a speed control system. This we'll study later. Temperature control system. This we have already studied. Drug delivery system is also an example of control system. You can draw this diagram. How to regulate the drug given to a patient through a drug tank, which is pumped to the patient through a drug pump, and the computer is used to regulate. Okay, so the reference blood level is taken as the input to the computer, which is now given to the output of the computer to the is given to the DAC, that is digital to analog compute converter, which is given to the drug pump. Then drug pump supplies the drug to the patient, and then patient's blood sensor is used to measure the blood pressure, and again converted, the signal is converted into an analog signal which is given to the computer. Right, so you can draw this diagram also. This is a good example of a control system. This is again, first you draw this.
Uh, 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 I want to ask, ma'am, aerospace and aeronautic engineering is a type of control system engineering. Hello, ma'am.
Yes.
Ma'am, I want to ask, ma'am, aerospace and aeronautic engineering is a type of control system
Yes,
engineering.
yes. Sure, this is a very major area of control systems. Controllers designed for attitude control of an aircraft. Major portion is control system. So this is the example of an aircraft turbojet engine in which the pilot command is given to a computer. DAC and ADC are used. The output is given to turbojet engine, which is used to uh, drive the aircraft. And aircraft state is taken and it is measured through aircraft sensors. Again, ADC. And before this, if you want to take the output from the engine state, that also you can take and measure it through engine sensor and feed it to the computer. So this is how we design the controllers for aircraft, airships, etc. Then robot manipulator is another example of a control system where the reference trajectory is given to the supervisory computer. The computer is given input to the manipulator, position sensor, velocity sensor, whichever we need. We take the output from the manipulator and feed it. If it is output is position, then it is fed to the position sensor. If it is velocity, then it is fed to the velocity sensor, and it is fed back to the computer. And robot manipulator is used for trajectory tracking. You can draw this diagram also. Okay, you can write down this. Meanwhile, I'll take your attendance.